Welcome guys to my third class of inner product space. In the second video already I started Pythagorean theorem, but this theorem is not complete in that video. Therefore I'm going to repeat once again for this. What about Pythagorean theorem? Now suppose u and v are orthogonal vectors in V. V is a vector space over a set of real numbers with dimension is a n or 2 or a Euclidean space. Then norm of u plus v whole square must be equal to norm u square plus norm v square. Observe carefully, u and v are two vectors in your inner product space. Then both u and v are orthogonal. Orthogonal means what? Inner product of u and u comma v must be equal to 0. Now from the definition of, now I have considered left hand side norm of what about u plus v whole square. From the definition of norm, you already have no need to write a square root in the right hand side because you already have a square in the left hand side. Inner product of u plus v comma u plus v. Now I am going to use from the definition of IPS. Don't confuse, IPS means inner product space. This is not a standard notation. For my convenient, in every place I want to write from the definition of product space, therefore I use IPS. Then don't confuse, but don't use the IPS word in your while writing a test or exam. That's because that is not a standard notation. Now from the definition of IPS means, here we are using additivity in the first slot. Additivity in the first slot, you treated this as one of the vector. Then what we get actually u comma u plus v plus v comma inner product of u plus v. Next you go for additive for these two. Additive inverse additive for in the second slot, additive for the second slot. From that u comma u, inner product of u comma u plus inner product of u comma v. Similarly, inner product of u comma v comma u plus inner product of v comma v. But you already know that from the definition of inner product, u comma v is same as v comma u. And also they given u and v are orthogonal. Therefore, what's the inner product of u comma v must be equal to 0. Now these two terms are 0. The remaining inner product of u comma u and inner product of v comma v. From the definition of norm, this can be written as norm of u square plus norm of v square. Therefore, finally we get norm of u plus v whole square is nothing but norm u square plus norm v square. Please try to understand that this is true only the case both the vectors are orthogonal in the inner product space. Okay. Now I'm moving to the next result. This is a one of result. They're going to ask the question in the exam or maybe in the test. The result is, if S is having n vectors, say v1, v2, etc., vn, is an orthogonal set of non-zero vectors. Is an orthogonal set of non-zero vectors in an inner product space V or R power of n. Because here having n the n vector C is a S is an orthogonal set of non-zero vectors in an inner product space V or R power of n or V of R power of n. Then S is linearly independent. Then I have to show that S is linearly independent. Hence S is a basis for V. Yeah. Now they given S is having n vectors, is a orthogonal set of is a non-zero vector, is an orthogonal set of non-zero vectors in an inner product space V of R power of n or just R power of n. Then I have to show that S is linearly independent. Once you show that S is a linearly independent, then hence S is a basis. Clearly, immediately S is a basis for inner product space V over R power of n. Now this is one of important result. First I have to show that this set S is a linearly independent. You know already basic definition of linearly independent pair in vector space. Same concept. Now given S is an orthogonal set of non-zero vectors. That is, what's the meaning of is orthogonal set for S? Inner product of Vi comma Vj equal to 0 for I is not equal to j, means mutual vectors of inner product must be equal to 0. and then inner product of vi comma vj must be greater than 0 because non-zero vectors. Now I have to consider what's the meaning of linearly independent, and then I have to write linear combination of these vectors, say c1 v1 plus c2 v2 plus etc. cn vn equal to 0. Then I have to show that each ci must be equal to 0. Then we say that these vectors are linearly independent. But I want to show that it's a linear independent based on the definition of inner product space. Okay, let c1 v1 plus c2 v2 plus cn vn must be equal to 0. I consider, because I want to prove that all Ci is 0, then we say that v1, v2, etc. vn are linearly independent. Okay. Now, therefore, I consider this equal to 0. Now, I consider, say, one of the inner product of C1, v1 plus C2, v2, etc. cn, vn, comma, this one vector, comma, vi equals, from what we assume that this sum of these values must be 0, comma, vi. Now, this is 0, you already known that. What about fourth axiom or fourth condition of inner product space? Inner product of 0, comma, alpha is equal to 0 or alpha, comma, 0 is equal to 0 where alpha is in inner product space. Therefore, from that axiom, because V is an inner product space, this value is 0 for every I. Okay. Then I am going to simplify this. From now I am going to take a second axiom or second condition of additive property in the first slot is nothing but first slot, and also I am going to take another homogeneity in the first slot. To combining both the things, please try to understand. I consider second and third axioms, means addition in the first slot and also homogeneity in the first slot. What we get? C1 into V1 comma Vi, C2 into V2 comma Vi plus etc. plus what we get actually Ci in between that. Ci is where one of the vector Ci of Vi comma Vi plus etc. plus Cn of Vn, inner product of Vn comma Vi equal to 0. Simply I written from the definition of inner product space. I explained here what are the condition axioms or conditions 2 and 3 of the definition of inner product space, because you already given V is a inner product space. Okay. Now see from the definition, because they given already S is a what actually orthogonal set. Therefore inner product of V1 Vi, V2 Vi, etc. Vn Vi all are 0 from the definition of orthogonal set except Vi comma Vi. Therefore this term is remaining Ci into Vi comma Vi equal to 0. But they already given S is an orthogonal set and also they given non-zero vectors. These vectors are non-zero vectors. If you want to add, and also what actually Vi is greater than 0. I think it's clear. Vi is greater than 0. Yeah, they given already each v1, v2, etc. Vn are non-zero vectors, means v1 is greater than v2 greater than 0. Every vector Vi for every I for I1 to n is greater than 0. See, product of two value is 0 means at least one must be 0, then only equal to 0. Now, from the given, Vi is not equal to 0 because Vi is greater than 0. It's a non-zero vector, therefore Vi is greater than 0. That implies what we are going to say, that Ci must be equal to 0 because product of two values 0 means at least one value 0. Inner product of Vi comma Vi is not equal to 0 because they given vectors are non-zero vectors. Therefore, I written and Vi is greater than 0. Therefore, Ci is equal to 0 for every I. Therefore, now we already taken beginning C1 or V1 plus C2 V2 plus etc. Cn Vn equal to 0. After you obtain the inner product definition, finally we get Ci's are 0 for I is equal to 1 to n, means for every I. Therefore, from the definition of linearly independent, clearly we say that S is linearly independent. I think everyone is clear, is linearly independent. Next, see what we get conclusion. S is having a set of n non-zero vectors. These vectors are taken from the inner product space V of R power of n or R power of n. These vectors are orthogonal set. What they consider vectors for S is an orthogonal set, and also these vectors are non-zero vectors. So they are taken from the inner product vector space V of R power of n. Then we say that vectors are linearly independent. We prove that whenever we get this type of vector, immediately write, no need to verify. From this result, they are linearly independent. How? Because just now I proved that whenever the given set, orthogonal set is orthogonal set narrated from any inner product vector space, these vectors are non-zero vectors, then clearly write these vectors are linearly independent. Next, and hence these S is a basis. And S is a basis for V. See, anyway is already verified that what you have orthogonal set for S is linearly independent. It is enough to show that it's a span. Means S is span of V. We know that S is a basis for V means S is linearly independent and S spans V. But we already verified that S is a linearly independent. No, only I have to show that it is enough to show that S is span V. S is span V means, it means that choose any vector in vector space, in a product space, that can be expressed as a linear combination of S. Then only say that S is a span of V. Now I have to choose one of the vector in inner product space, V belongs to V. Then it can be written uniquely in the form of V is equal to C1 V1 plus C2 V2 vectors of S, etc. Cn Vn, where Ci's are scalars. Then I consider, please try to span means I choose any vector in V that can be written as linear combination vectors of S. Then we say that S is a span of V. Now I consider inner product, but I want to prove that based on the definition of inner product. Therefore, inner product of V comma Vi is one of the vector from V1 to Vn. Now we already taken what is V, C1 V1 plus C2 V2 plus etc. Cn Vn comma Vi. Using the second and third axioms or condition of inner product space. Now what we are going to write, C1 into V1 comma Vi, what we just now discussed in proving of linearly independent, plus C2 into V2 comma Vi plus etc. Ci into Vi comma Vi plus etc. plus Cn into Vn comma Vi. But you already known that V1, V2 etc. Vn are all linearly, they are linearly independent, and also these vectors are what type of vectors? Orthogonal vectors. That S is nothing but orthogonal set means mutual inner product value must be 0. Means inner product of V1 comma V2, V2 comma V3 like that is 0 except Vi comma Vi. Therefore, what's the remaining? Ci into Vi comma Vi. Are you clear or not? Now V is equal to Ci into Vi because I written since S is an orthogonal set and also Vi is greater than 0 for every I. Therefore, from this V is equal to Ci into inner product of Vi comma Vi. Therefore, what is my Ci is, I'll take this as a cross multiplication for this inner product of V comma Vi divided by Vi inner product of Vi comma Vi. Inner product of Vi comma Vi is nothing but norm of Vi square for every I. See, now here we get the values of scalar values of C1, C2, C3 in terms of V. In terms of V, right? What is in terms of V? Inner product of V comma Vi divided by norm of Vi square for every I. You put I is equal to 1, we get C1 formula. We put say I is equal to 2, like that we get up to Cn formula. This implies that V is a linear combination of vectors of S. Therefore, S span V. Therefore, S is a basis for V. This S is also called an orthogonal basis for V because S is having a vectors. What type of vectors you have? Orthogonal set vectors. The corresponding basis is called orthogonal basis for V. Please try to understand the entire thing is here they given S is having n vectors. These vectors are orthogonal set vectors and also non-zero vectors in a vector space over a set of real numbers with dimension n. Then first I have to show that S is a linearly independent. We how to prove that? First I have to take linear combination of these of the vectors. Choose one of the vector. C1 V1 plus C2 V2 etc. Cn equal to 0. Then I have to prove that Ci is equal to 0. What I did? I take inner product of this entire vector comma one of the vector from V1 to Vn is Vi. Now I have to use the second and third axioms or conditions of inner product space. I simplified that, and after that I applied the definition of orthogonal set. Finally is remaining Ci into Vi comma Vi equal to 0. But they given already vectors are non-zero vector, therefore Vi is not equal to 0, Vi is greater than 0. Therefore only which one is 0? Ci is 0 for every I. From this we get given orthogonal set vectors are linearly independent. Next I have to show that these non-zero vectors of orthogonal set is a basis for a corresponding inner product space. It is enough to show that S is a span of P. S is a span of P means it is enough to show that S is to choose any vector in a V that can be expressed in linear combination of vectors of S. Therefore, now I choose one of the vector V belongs to V. V can be written as linear combination of these vectors. Then I have to consider V comma one of the vector, say Vi, inner product, because I want to prove based on the inner product. And then again I have to apply the conditions second and third and simplify that. Finally we get CNT inner product of Vi because V1, V2 etc. Vn are orthogonal vectors, means inner product of Vi comma Vj equal to 0 for I is not equal to j. After the simplification, we get Ci. What is Ci value here? Ci is inner product of V comma Vi divided by norm of Vi square. Now, for I is equal to 1, we get C1, I is equal to 2 like that. Now, we get C1 in terms of V. Then we say that V is a linear combination of vectors of S. Therefore, S is span V. Therefore, S is span V, S is a linear independent, therefore S is a basis for V. This basis is called orthogonal basis of basis for V because this is a orthogonal set. I think it's very clear. Before going to wind up this, keep in mind whenever set is orthogonal set is a orthogonal basis means that scalar can be expressed as inner product of V comma Vi divided by norm of Vi square for Ci for I is equal to 1 to n. You remember this. From this formula only I have to find out C1, C2, C3 to express the linear combination of orthogonal vectors for the vector space, inner product space. I think everyone is clear how much important for vector space. Without understanding vector space, you are not understanding anything. I think everyone is clear for this. Now I'm going to wind up my class. I'll come and meet in the next video for some more problem based on that. Please remember what's the meaning of orthogonal set, what's the meaning of orthogonal basis for the inner product space. Thank you very much.